Okay, so in today's discussion, we will start with Switch. Okay, and before we jump into the discussion of Switch, just let's simply understand a small history behind why Switch was created. Okay, and what was the purpose of its creation, and how is it helping in today's networking? So we know that computers were created even before Switch was created. Right? So computer was the first intelligent device that a human had created long back, and human had created a computer to do faster mathematical calculations. Correct. So let's suppose I had one computer created and I had another computer created, right? So these two computers were able to do faster mathematical calculations, not just mathematical, a lot of other calculations, right? And then we thought that two computers should be able to communicate with each other or share their information with each other. So what happened? We had to join them together through a cable, right? Then what happened, as more and more computers started to come up, right? We thought let's join them, or let them share the information together, right? And each of them let them share the information with each other. Each computer will share the information with each other. Now here what is happening? There are one PC number one. Okay, it needs to have connectivity with three other PCs, right? So basically what is happening, one PC should have three connectivities, or basically it should have three ports. So here if you see, just for four different PCs, we would have 12 different connections in the network, right? We will have 12 different connections in the network so that all these computers can talk to each other. Now when computers were created, having a port itself was a huge a huge task. I'm not sure if you had seen some pictures on the internet. A small a 2 MB of a hard drive was a huge it was a huge device, a storing device. Just it can store only 2 MB of data, but it was a huge device, right? And imagine computers as we see now. Back then, computers did not had any screen. They were all mechanical devices, which were mechanical devices which had electrical components inside them, which could do faster calculations. Okay. Now, if you want them to share information, you should create some kind of cabling so that they are able to transfer. Now, in this case, if you want to create, if you want to share information with three other different computers, you need three different ports. And back then, creating three different ports again was a tougher task. Imagine not just three, you have hundreds of computers in the same room. So you need 99 different ports in order for you to exchange that information with the other computers. So it's going to be a tedious task, right? So in order to solve that problem, we came up with a simple device, which was called as hub, a hub, right? And the purpose of the hub was, if you connect all the computers to a hub, what it will do is, if PC number one sends a data, right? What hub is going to do? Hub is going to copy that data and create multiple duplicate copies of that same data and forward it out of all the other interfaces, right? So even if you have 99 devices connected, if you have 99 devices connected to this hub, all that hub can do is it will copy that data and forward it to everyone. It was a very simple task. Okay. Now then what happened? We wanted that, let's say that these two PCs or computers are part of, let's say IT department, for example. Okay, and these two PCs are part of, let's say, HR department. And as need started to come up, we said that the PCs in the IT should be able to talk to each other. Okay, so that means if PC number one sends a computer number one sends a data, right? It should only be received by computer number four. However, with hub, the problem was it would be sent to all the devices, right? That was a problem. And even now there is a it's called as a repeater. Okay, there is a, instead of hub we call it as a repeater, where if it receives a data it will send it across all the devices. Okay, and such kind of devices nowadays in present networking terms are called as unmanaged devices, unmanaged switches. Okay, so unmanaged switches which are not actually hub, they have some kind of intelligence. However, their main work is like you have some connected, let's say you are an owner of a internet cafe, right? You are getting internet. What you would do is you would connect your internet cable to this unmanaged switch, where it will have multiple ports. Okay, it will have multiple ethernet ports, and you can connect these ethernet ports to different devices. From, you can connect it to a wi-fi router, you can connect it to your laptop, you can connect it to your pc, or you can connect it to your ps5, etc., a lot of things. So basically what is happening, whatever data is coming into this interface, it is sending it out of all the other interfaces. Okay, so currently you have such unmanaged switches which are basically working as a hub. So in olden days, we wanted that two different, like not all computers should be able to receive that information, and hub is not able to do that. So what we did, we created another device. This was the first intelligent device in the networking side, which we now call it as a switch. Right. So if PC1 sends a data, switch will read that data and forward it to the desired PC. Now the interesting thing comes, based on what is it forwarding the data, right? So if the switch wants to forward the data to only computer number 4, it should have some kind of information or relevant information that it knows exactly that this computer only needs that particular data, not 2, not 3. It only should be sent to computer number 4. And what was that information that the switch reads? Can anyone tell me? It's a very simple question.
MAC address.
Exactly. Right. It needs a MAC address. So the switches, they need a MAC address to forward data. So without a MAC address, the switches are not able to forward data. Right. So what happened was PC number one, let's imagine PC number one has a MAC address of 1111. PC2 has 22222. This has 33333, and PC number 4 has 44444. Right. So just like we write a letter, where we when we are writing a letter, we give a to address, and when we also give a from address. So when the PC is sending a data to PC number 4, all it needs is, it is being sent by 1111, not 1111, sorry, 4444, right? And it is from 1111, right? So when the PC sends this data to the switch, switch will read the MAC address, okay, inside its MAC address table, and based on the MAC address table and its information, it will forward the data to the PC number 4, right? So with this, we come to know that switch is one of the first intelligent devices that was created in networking, and also it needs a MAC address to forward data, right? Now we all know that. Do I have to explain what is a MAC address? I think everyone, right? What is a MAC address and how does it look like? So basically, MAC address is a 48 bit, yeah, 48 bit. What do you say? A 48 bit field. Okay, it's a 48 bit field, right? And a MAC address usually comes in the layer 2 of your OSI layer model, or your TCP IP layer model. Okay, so in the layer 2 of an Ethernet header, it acts as a 48 bit field, right? And basically it's a hexadecimal digit. So if we open up my Wireshark, right? So if you see here, this is a MAC address. right? This is a MAC address 70B6 4F6C A346 and F4 A4 75072E6B. These are MAC addresses, right? There are different types of not different types of MAC addresses. There are different combinations of MAC addresses, and they are created using uh, a unique, like organizationally unique identifier plus some other combination of numbers, right? So I'm not going to go in depth over that. However, I just wanted to let you know that a MAC address basically looks like this. It's a hexadecimal number. Okay. And when I say hexadecimal, one digit, let's say this, it was 70, right? So this is a 4-bit number and this is a 4-bit number. Okay. So this 0111 and 0000. Okay. Yeah. So this is your hexadecimal number that it's written as, right? Now, as I was saying that with switch, okay, we need to understand that when from a real time perspective, right, even when someone comes to us, let's say we are walking on the road and someone comes to us and says, I want to, I live in Pune, right? Someone comes to me, he is coming from, let's say he's coming from Bangalore, right? And he asks me, I want to go to Pune. Sorry, no, I want to go to Bombay. Do you know how to go? Right. So until and unless I know how to go to Bombay, or until unless I know the direction to Bombay, I will not be able to tell that person. Right. First thing. Second thing, if I know how to go to Bombay, I will direct him. This is the way you have to go to Bombay. Right. So these are the two factors that I would use in my real-time experience as well. If someone comes to me and asks, and if I know how to reach the destination, I will guide him. If I do not know how to reach the destination, I will tell him, go ask someone else. Correct. So these are the two criteria that I would use. It's a similar criteria that a switch would basically use to forward data. Right. So let's imagine that I have a switch over here. Right. Now let me connect different PCs, PC number 1, PC number 2, PC number 3, and PC number 4. Now, we also know that a switch has its own table, right, which is called as a MAC address table. Right? And in the MAC address table, it has two major columns. One is a MAC address column, and the other is a port column or an interface column. Okay. So this is interface number 1, 2, 3, 4. So what this diagram says is PC number 1 is connected to the interface number 1 of switch number 1. And PC number 1 has a MAC address of 1111. PC2 has 222, 333, and 444 respectively. Okay. Now, let's say that PC1 wants to send a data to, let's say, PC number 3. Okay. So when it is sending a data to PC number 3, right, it will create it will create an Ethernet frame. Since we are talking from a switches perspective, we are only considering and concentrating only on layer 2. Okay. So we will have a source MAC address, correct? PC number 1 will say, I have a source MAC address of 1111 and I want to send the data to PC number 3 with a destination MAC of 3333. Now, we are assuming that all the PCs, they know each other's MAC addresses, and switches MAC address table is completely empty. These are the two assumptions that we are doing, that all the PCs, PC number 1, 2, 3, 4, they know about each other's MAC addresses, and switch does not have any entry in its MAC address table. It's completely empty. This is what we are assuming. Okay. Now, when PC number 1 sends this data, right? So what the switch does is, the switch, first of all, it learns the MAC address. Okay. Now, how it learns the MAC address is that it learns the MAC address based on the source MAC address. So here, the source MAC address is 1111. So it makes a note of it that I have received a data with a source MAC address of 1111, right? And on which interface have I received it? I have received it on interface number 1. So it makes an entry. Then the second, it looks where is this packet to be sent to. It is to be sent to a destination MAC of 3333. But do I have an entry of 3333 in my MAC address table? No. As per our assumption, it does not have an entry. So this is the first criteria where a person comes to me and asks, do I he wants to go to Bombay. If I do not know how to go to Bombay, right? Or if I do not know the direction, what I would say, go ask someone else, right? This is what the switch is going to do. He would say, I do not know how to reach 3333. What I would do is I would tell him to go ask anyone else. I do not know. So basically, instead of sending him forward, what the switch does is switch will make a copy of it, make a copy of this packet, and will broadcast it out of all the interfaces. Okay, so it will send it out of interface number 2, interface number 3, and interface number 4. Now, this packet is received by PC number 2, is also received by PC number 4. Now, one PC number 2 and PC number 4, they receive it. They see that is this packet for me or not. And how do they check? They check it through a destination MAC address. Right? So PC number 2's MAC address is not 3333. So what it will do, it will basically drop this packet or basically ignore the packet. It's not going to respond to this. Similarly, PC number 4 is also going to drop this packet or ignore this packet because the destination MAC is not 3333 and hence it will drop it. The only PC which is going to respond to this information is PC number 3, because when this data is received by PC number 3, it checks the MAC address, right? And it sees that this packet is for PC number 3, right? Now, when PC number 3 wants to respond, now let's say PC number 3 got the information and it wants to respond to PC number 1. So it creates a packet with a source MAC of its own MAC address and a destination MAC of 1111, right? And it will send it to the switch, not the switch, it will send it out of its exit interface, right? Now, this message or data is received by the switch. Now, whenever a switch receives a data, it will always read the MAC address. Be it the same data, be it a different data, every single time a switch will read the MAC addresses, and it will always read the source MAC address, not the destination. It will always read the source MAC address. So now the first thing that the switch does is it checks, does it know about the source MAC address 3333? No, it does not have an entry of 3333 in its MAC address table, right? So it makes an entry. Okay, saying that I have received a data with a source MAC of 3333 on the interface number 3, right? Then second thing it checks, destination. Do I know how to reach the destination MAC address? Yes, I know how to reach the destination MAC address. If I want to reach the destination MAC address of 1111, I have to forward the data out of interface number 1. And thus the switch forwards this data to PC number 1, and hence PC number 1 receives this information. And this is how PC number 1 and PC number 3 are able to talk to each other. Okay. Now the next time when PC number 1 sends the same data, okay, when PC number 1 sends the same data, let's check what PC is going to do. So the switch receives this packet, it checks for the source MAC address. Does it have the entry of source MAC address in its MAC address table? Yes, it already has it. Then, does it know how to reach 3333? Does it have an entry? Yes, it knows how to reach 3333. That is out of out of interface number 3. So it will forward the data to 3 directly instead of forwarding the data out of all the other interfaces. Okay. This is how, when a switch does not know about the MAC address, it will broadcast it out of all the interfaces. And when it knows about the MAC address, instead of broadcasting, it will check its MAC address table and forward it to that desired through that desired interface. Okay. Any question, or does anyone want to add something here?
Yeah, Lakshya. As far
Yeah.
as my understanding is like, whenever a PC first time making a connection with a switch with some destination, it will send its own source MAC address along with FFFF broadcast as a destination. Okay, destination
Yeah,
MAC
yeah.
as a
So
broadcast.
as
Then
I
it will,
said,
yeah,
correct. You're
then it
saying, yeah.
will,
So what I think you joined late. So what I said is, we are making two assumptions. First assumption is
okay,
that all the PCs, they know about each other's MAC.
okay,
That was my first assumption. Second assumption is that the switch does not know any MAC addresses.
okay.
PCs know about each other's MAC address. Switch does not know about anyone's MAC. So what you're
Yes,
saying is about GR. We'll talk about GR later when we are
yes.
talking about
Lakshya thought, yeah.
R. Yeah. So any other thing? Anyone?
I'm good.
Okay. Now let's say if PC number 4 wants to send data to PC number 2. Okay. So the source MAC is going to be 4444, right? Destination MAC is 2222, right? Now this data is sent. So the first thing that the switch checks, does it know the source MAC of 4444? No, it does not know. So it makes an entry. It was received on interface number 4. Then does it know about the destination MAC 2222? No, it does not have any entry in its MAC address table. So here again, what the switch is going to do, switch is going to basically broadcast it to all the other through all the other interfaces. PC number 1 and PC number 3 are going to ignore it because that's not their MAC address. The only PC which is going to accept it is PC number 2, right? Now PC number 2 accepted the data and it will send back the information, or it will respond, right? When it responds, it will have a source MAC of 2222 and a destination MAC of 4444, right? And it forwards the data. Now the switch receives it. It checks the source MAC. Does it have an entry of the source MAC in its table? No. So it makes an entry. Then it checks, does it know about the destination MAC? Yes, it knows about the destination MAC, and it should be forwarded out of interface number 4. And it will forward it to PC number 4 like that. Right. So with this, in layer 2, we understood few different types of traffic. So when you're troubleshooting, right, they will use different kind of terms, right? Unicast, broadcast, unknown unicast. So the moment you hear these terms, right, you should be able to answer. And even sometimes in in interview, they say these. It's a unicast message, right? It's an unknown unicast or it's a broadcast. So you should be able to visualize what is a unicast, what is a broadcast, and what is an unknown unicast. So let's write that down. Unicast. Okay. Unicast meaning there is one, there is a source MAC address, okay, like 1111, and a destination MAC address. Okay, 3333. Okay. So this is a unicast. One-to-one communication is happening. Right. Then the second is a broadcast. Now, in our earlier, whatever hypothetical situation I was saying, I did not show you the broadcast. However, in an actual broadcast term, what happens? There will be a source MAC. Okay, it can be any source MAC. Okay. However, the destination MAC is going to be a broadcast MAC address, and the broadcast MAC address is all F. Okay. This is a special, this is a broadcast. where the destination MAC is FFFF. That means it's broadcast. Then the third is called as an unknown unicast. Okay, where it is a unicast, meaning that it will have a source MAC address. It will also have a particular destination MAC address, let's say 4444 and 2222. Right? It is a unicast. However, it is unknown. Unknown for who? Unknown for the switch. Meaning that in the switch's MAC address table, right? In the switch's MAC address table, this destination MAC is not present. It does not know how to forward this data because it does not have an information about the destination MAC address, right? Because that destination MAC address device has not sent any data yet. Until and unless, we know that until and unless a data is received by the switch will never make an entry. Okay, this is what we have learned till now. A switch will always make an entry when it receives the data, and when it receives the data, it makes an entry of the source MAC address, not the destination MAC address. Okay, and with the source MAC address, it populates its MAC address table. So here what is happening? Unknown unicast, meaning that this guy, whatever device with this MAC address has not yet sent any data to the switch. And that is why switch was not able to make an entry of it. And because it was not able to make an entry of it, this MAC address is unknown to it. And when it is unknown, we saw it in our example, when a particular MAC address is unknown, the switch basically broadcasts it out of all the interfaces. Right? So an unknown unicast, a switch treats it as a broadcast only. However, the MAC address is not FFFF. The MAC address is not known by the switch. That is why it calls it as an unknown unicast. Okay, any question with this three types of layer 2 traffic? Okay, I have been asked this question long back, but just once or twice. What are the different types of layer 2 traffic in networking? Okay, what are the different layer 2 types of traffic? So you have a unicast traffic, a broadcast traffic, and an unknown unicast traffic. Okay. Any question with this?
So multicast is not part of it?
Multicast, again, okay, since you have brought it, good, let me discuss that also. Okay, if you know about multicast, we have heard about multicast addresses during our IGP protocols like OSPF. Okay, we know that OSPF has a multicast address of 224.0.0.5 and 6, right? EIGRP, right? It has a multicast address of 224.0.0.10, right? If I'm not wrong.
Yeah.
10. Yeah. Then MPLS, I think, not MPLS, LDP. LDP has a multicast address of 224.0.0.2, right? Even HSRP. HSRP also has a 224.0.0.2. However, the port numbers are different for these. Okay, it has a different port number. This guy has a different port number. The multicast address remains the same. Now, what is this multicast? What is this multicast? Okay. Unicast. Okay. Unicast is one-to-one communication. Broadcast is one-to-all. One-to-all. However, multicast is not one-to-one. It is not one-to-all. It is one-to-many, not all. Many. And how is that many defined? Many is defined by the protocol that is being defined on the device. For example, if a router has been configured with OSPF, it will understand OSPF information. If a router has been configured with EIGRP, it will understand EIGRP information. If it has been configured with LDP, it will understand LDP configurations or LDP message. Basically, every routing protocol has its own language. For example, consider this as Hindi. Okay, this as English. Okay, and this as Tamil, for example. So if two people know Hindi, understand Hindi, they can talk to each other. Similarly, if a person speaks English, he can he can understand anyone else who is speaking English. Similarly, it goes for Tamil also, right? Now, two different language speaking people cannot talk to each other. Why? Because they do not understand. So here, what is happening? Hindi speaking people have formed their own group. English speaking people and Tamil speaking people have formed their own group respectively. So this is what you call it as multicast. Okay, it is not everyone, and it is also not just unicast. It is similar people with having similar features and properties. They are able to talk to each other. So for that purpose, we created something called as multicast addresses. And for different protocol, different features, different users, we created different multicast addresses, starting from 224 of your IP address range up till 239. Okay, so this is your multicast address range. Now, a switch, specifically a layer 2 switch, which understands only MAC addresses. Okay, multicast addresses have their own multicast MAC addresses. Please remember, multicast IP addresses have their own multicast MAC addresses. Remind me if I have time. What's the time? 9. Okay, if I have time, I'll explain this. Okay, as I was saying, every multicast IP has its own multicast MAC address. So OSPF has its own multicast MAC address. EIGRP has its own multicast MAC address. LDP will have its own multicast MAC address. HSRP will have its own multicast MAC address. Okay. Now, any layer 2 switch, like what we have been seeing here, any layer 2 switch cannot understand the multicast addresses, cannot understand the multicast MAC addresses. Okay, so when it does not understand a multicast MAC address, it will always treat as a broadcast. So a switch, specifically a layer 2 switch, that is why I'm specifying this layer 2 switch, it will always treat a multicast MAC address as a broadcast address only. So let's say if, for example, there is, instead of a PC, imagine this as a router, and on that router, okay, let's say on all these routers you have created OSPF. So when you create OSPF, obviously it will send hello messages, and it will send hello messages at the multicast address of 224.0.0.5 along with its multicast MAC address. This is at the layer 3. At layer 2, it will have its own multicast MAC, correct? Which it will be sent. Upon receiving, the switch will not understand this multicast MAC address. It cannot comprehend. A layer 2 switch will never be able to understand the multicast MAC address, and what it is going to do, it will forward it to all the different routers that is connected to it. So a layer 2 switch can understand unicast MAC addresses, broadcast, where the destination MAC is specifically a broadcast address. It treats unknown unicast as a broadcast, and it also treats multicast MAC addresses also as a broadcast. Clear? Any question?
All good, Lash.
All good.
All good. There is one more. I'm not sure because in my previous company I have heard is Anycast. Known Unicast, or it is used in data center technologies.
Anycast, yeah, I have
Yeah.
heard Anycast. I am not completely aware of this thing,
Yeah,
so I cannot discuss
it
that.
it is used in VXLAN technology.
All right. Okay. Okay.
Only this much idea I have.
As I said, I do not have much idea about
Okay.
this. So if anyone wants to read about it, please go ahead. No problem.
Okay.
Now, as I was saying, it's an it's the topic that I'm going to tell you now will never be asked in any interview question. However, it is good to know
Yeah.
how to find out the multicast MAC address of a particular multicast IP.
Hmm.
Okay, let's discuss that. So we know that for OSPF, the multicast IP address. Okay, Mohit, are you able to get this? Whatever I'm saying. Any questions?
Yeah, I'll have to go through the video again. I am getting lost while you were teaching multicasting.
Okay, yeah. Multicast is anyway a bit of an advanced topic, so it's okay. No worries. Now, all right. So we know that for OSPF, the multicast IP address is 224.0.0.5. Okay. Obviously, if it is a multicast IP address, there should be a corresponding MAC addresses. Okay. So because obviously, when a particular router is reading the information, it reads to layer 1 and layer 2, layer 3, layer 4, etc. So obviously at layer 2, it would have a source MAC address information and a destination MAC information also. Correct. And the destination MAC address is always corresponding to the destination IP address. And when OSPF is sending its hello messages, it will send the hello message at the destination IP of 224.0.0.5. So have we ever seen an OSPF router creating an ARP request? No, right? That means obviously there would be a particular MAC address for this IP address, right? And that is what we are going to discuss now, how to find that out. All right. So first of all, what you're supposed to do is that you're supposed to, first step, convert all this decimal number to their equivalent binary format. Okay. So when you convert them into their equivalent binary format, let me open up the converter on Google. 224. Okay, so it is 111 and 50. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, and this is 0, 1, 2, 3, 4, 5, 6, 7, 8. Again 0, 1, 2, 3, 4, 5, 6, 7, 8, and this is 1, 2, 3, 4, 0, 1, 0, 1. Okay, so this is your first step of converting your IP address into their respective binary format, 8-digit binary format. Okay, that's the first step. Then what you're going to do, you're going to take the second step is take the first 4 binary digits, that is 1110. Okay, take the 1110 over here and write it as 00. Uh, 01005. Zero one zero zero five E. Okay, convert this. Okay, the first 4 digits of any multicast MAC address. It can be 224, it can be 225, 226, 227, up till 239. Any IP address starting from 224 up till 225. Okay. The first 4 digits is always going to be 1110. Okay. Because 1110, then these 4 zeros is 224. So if you want 225, you will convert this to 1. If you want 226, you will convert this to 1. 227, this. So all that will change. But the first 3 digits, sorry, not 3, 4 digits of numbers from 224 up till 239 will always remain the same. That is 1110. So what you're first going to do, first convert any multicast MAC address into their respective binary format. Okay. Then take the first 4 digits and write it down as 01005E. That is the standard format that have been designed. Okay, you can say that. So 01005E, then these are 4 zeros over here, 1, 2, 3, 4. Over here, these are 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8. Then again 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8. Then 1, 2, 3, 4, 0, 1, 0, 1. Okay. This is how you write. Then the third step over here is that take the next 5 zeros, that is this 0 and this 0, and write it as a single 0. Okay, take this 5 digits of zeros, or it can be any number also. If it is 239, yes, it will have some other number. In this 4 digits, it may have some other number, right? So no matter what the number is, take the next 5 binary digits, right? And replace them with a single 0, meaning 01005E. Then this 4 zeros and 1 0, write it down as one single 0. Right? Then write the next few, write the next binary numbers as such. So you have 7 zeros over here, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 0, 1, 0, 1. Okay. So this is how you are separating them. Then the fourth step is convert them back to their hexadecimal format. So it is 01005E. This would be 0, 0, right? And then 0, 0. This is again 0, and this is 5. And let's check on Google. You see 01005E 000005. And that is what we have. So here, let me again explain what you're doing. Convert your decimal numbers into their respective binary format first. Okay. Then the second step, take the first 4 digits of that binary number and write it down as 01005E. Then continue the next binary numbers as such. Right. Third step, take the next 5 binary digits and write it down as a single 0. And then copy all the next binary digits as such. That is third step. Fourth step, convert them back to their decimal form. And that is how you get the multicast MAC address. You can do this for anything. It can be a let's say 228.9.3.2, for example. This is a multicast MAC address, for example. You can find out the multicast MAC address for this using the same step. So when you're troubleshooting, you should know this conversion, if that conversion has done properly or not. Sometimes because of a bug, because of a glitch, the multicast MAC address is not created appropriately, and because of that, your multicast may have a problem. You should know how to convert it. If you do not understand, it's okay. When the recording is available, go back to the recording and watch this. You'll be able to understand. Okay, I'm not sure how many of you got this. Did anyone understand? Not understand?
Yeah, it's easy to understand.
Okay. Now, moving on with our topic today. So switches, right? Multicast MAC addresses, unicast, broadcast, and unknown unicast. Now, as things started to develop, we said that I want, even with the MAC addresses, I want that similar department, PCs in the similar department should be able to communicate with each other, and PCs in different departments should not be able to communicate. Right? So here we have a switch. It's connected to PC number 1, PC number 2, PC number 3, and PC number 4. Okay. So I said PC number 1 and PC number 4 are part of the same department. PC number 2 and PC number 3 are part of the same department. Okay. MAC addresses are there. Okay. And yeah, this is 4444. This is 2222. And this is 333. Okay. Let me draw the circle in some different color. All right. Now, instead of 4 pieces, let me draw a couple of more pieces. Piece number 4, this PC number 5, 5, 5, 5, 5, and this is PC number 6, 6, 6, 6. Okay. Now, all the PCs I have demarcated. Okay. These PCs are on the same department, and PCs on the left-hand side are on the same department. So now, instead of just imagining them 3 PCs, imagine there are 10 or 20 PCs connected in the same on the switch, and are a part of the same department. Now PC1 wants to send a data to all the PCs that are on the same department. He will have to create multiple unicast packets, right? So he will create a unicast packet with source MAC of 1111, right, and a destination MAC of 6666. This is one packet, and then similarly he will create another packet which has a destination MAC of 4444, right? So every time a PC number 1 wants to share the data to PC number 6 and PC number 4, it needs to create 2 set of packets. Imagine there are 10 PCs or 20 PCs, and in real time, sometimes on a switch, there are 50 PCs connected together, right? So if one PC wants to send data to all the other 50 PCs, it needs to create 50 different packets, right? It is going to, it's basically a very tedious task for the PC, right? So what we did, we said instead of having the PC to send multiple packets or multiple information to each and every single devices, let's create something called as a virtual LAN. Okay, virtual LAN, where different, not different, same PCs of where same PCs from the same department or PCs from the same department are grouped into are grouped into a particular VLAN, and PCs on a different from different department are grouped into a different. For example, these PCs on the left hand side are part of VLAN number 10, for example, and these are part of VLAN number 20. So now what this PC has to do? Okay, this I'm giving you a very hypothetical scenario. When we get into the detail, we'll understand PC is not going to do anything, but just for an understanding sake, let's from an understanding point of view, let's imagine this as a not imagine, consider this as a hypothetical situation. So now what PC has to do is PC just needs to add one information, source MAC 1111. Okay, then the VLAN number 10. Okay, then what the PC can do is it will send the data to the switch. Okay, whatever I'm explaining from a PC's perspective is absolutely not correct. That's not how the things work in real time. But just imagine that how things are easier with a VLAN. So what is happening is when PC sends the data, it adds a value of VLAN 10 to it. Right now, the switch knows PC number 6 is part of VLAN number 10. PC number 4 is part of VLAN number 10. It will forward the data to only those devices directly with just one single packet. Similarly, PC number 3 wants to send the data. It will send a data to VLAN number 20. So now the switch will send data to PC number 2 and PC number 5 respectively. And what is happening? They are not able to send data to each other. Their data is secured inside their own VLANs. And this is why we created VLAN this is why we created VLAN, so that we can separate domains, so that similar category devices can be placed into a VLAN and different category devices can be placed into a different VLAN. Okay, so first thing, VLAN helps in creating different domains, and that domain is called as a broadcast domain. Second thing, it somewhat acts as a security also, where PC number 3 belonging to VLAN number 20 cannot send data to PC number 1, which belongs to VLAN number 10. So what is happening? Inter-VLAN communication cannot happen. Because inter-VLAN communication cannot happen, there is a bit of a security that is added. And the example that I gave, where PC is sending a data on VLAN, which is not correct. Now let us look into an exact scenario of how VLANs are working using a switch. So switch PC1, PC2, PC3, and PC4. Interface 1, interface 2, interface 3, interface 4. Now, what I want is that PC1 and PC4 to be part of a VLAN. Okay, let's say VLAN number 10. Now, please remember, PCs do not understand VLANs. PCs, they do not understand your routing protocols. PCs do not understand VLANs. PCs do not understand spanning tree protocol, HSRP, whatever protocols that you think of. They do not understand those things. Okay. So when we are talking about VLANs, where are we configuring it? We are basically configuring it on the switch. Okay. And we are telling the switch that these two interfaces on you are part of this VLAN. So when I create a VLAN, I would say that you are part of VLAN number 10. This interface is also part of VLAN number 10. So basically what is happening, whatever device, it can be a PC, it can be another switch, it can be a printer, it can be an IP phone, it can be even your, if there is an Ethernet cable on your TV, and if you connect your TV to this interface of this switch, so switch considers whatever device is connected to this interface is part of VLAN number 10. Okay, the device is not part of VLAN number 10, but the interface where the device gets connected is part of VLAN number 10. Similarly, on interface number 2 and on interface number 3, we say that you are part of VLAN number 20. Okay, you are part of VLAN number 20. Now let's see how the packet flow is happening. So you have a MAC address column, you have a port column, and next now you also have a VLAN column as well. You have a VLAN column as well. Right. Now, as I said, we have configured on the switches VLAN number 10 and VLAN number 20. We will look at the lab tomorrow about this, but just consider this scenario where we have configured VLAN number 10 on the switch and VLAN number 20 on the switch. So now PC number 1, again, the assumption is all the PCs, they know about each other's MAC address, whereas the switch is completely unaware of that. So PC1 sends a data, right? So with a source MAC of 1111 and a destination MAC of 4444, because 4444 is part of the same VLAN, right? Now this data is received by switch. The switch, then what it does, switch will make an entry. It checks the source MAC address, right? 1111. On which interface was it received? It was received on interface number 1. And interface number 1 is part of which VLAN? It is part of VLAN number 10. Now, 4. Does it know about 4444 in MAC address table? No, it does not know. So now it is supposed to broadcast it. It is an unknown unicast. We just discussed unknown unicast, right? It is supposed to be an unknown unicast. Can now someone tell me how will the switch broadcast the packet? It is an unknown unicast. We know if it is an unknown unicast, meaning the destination MAC is not present in the MAC address table of this switch, the switch will basically broadcast it out of all the interfaces. Now in this scenario, how will the switch broadcast the packet? Can someone just give me a wild guess? Interface number 10, interface number 1, and interface number 4 are VLAN number. This is interface number 1, interface number 4, this is 2, this is 3. These two are VLAN number 20, these two are VLAN number 10. Can someone tell me how the switch is going to broadcast this packet? Anyone? Okay, no problem. So switch made an entry for it, right? Switch made an entry for VLAN. It says VLAN number 10. Correct. Now the switch will look for all the interfaces that are part of VLAN number 10. Again, I'm saying the switch will now look for all the interfaces that are part of VLAN number 10. And here, the interface that is part of VLAN number 10 is only interface number 4. And hence, this broadcast will be sent out of this interface. And it will not be sent to PC number 2 or PC number 3, because they both are, those interfaces are not part of VLAN number 10. They're part of VLAN number 20. And because there is only one interface which is part of VLAN number 10, that broadcast is received by PC number 4. Now, when the PC number 4 responds, it will have a source MAC of 4444 and a destination MAC of 1111, right? Now, when this packet is sent, back, switch receives the packet, it reads the source MAC address. Does it know about the source MAC address? No. So it makes an entry for it, and it was received on interface number 4. and interface number 4 belongs to VLAN number 10. Then it checks the destination MAC address. The destination MAC address, does it know about the destination MAC address? Yes. It also knows the interface. And the third thing that it checks is the receiving interface and the exit interface. The entry interface and the exit interface, are they part of the same VLAN? If yes, then only it will forward the packet. And here, yes, exit interface port number 1 is part of VLAN number 10, and hence everything is matching, and the packet is forwarded to PC number 1. Any question? Clarity, or anyone wants furthermore clarity over here? We can discuss this. Because based on this scenario, or whatever I'm saying, we'll discuss another important interview question.
Lakshar, I have one doubt. Okay, I don't know
Yes.
that exact term. So there is a one term split horizon in BGP. Okay, where like a broadcast is it's something which is receiving from the interface. So suppose that switch or router want to broadcast, it won't send that packet again to the means broadcast packet to the receiving end interface. So what it call exactly? Because I like in so some of the interview, someone asked me this question related to the switch. I don't know exact word. Like split horizon is in BGP, right?
No, split horizon is a very common term.
Mm-hmm.
Okay. Split horizon means whichever interface that the device received the data, let's say over here. Okay. Here, the data is received by the switch on interface number 1. Okay. And if it wants to broadcast this packet, right, it cannot send it back via the same interface. That is split horizon. So जिस इंटरफेस से डेटा रिसीव हुआ है उसी इंटरफेस पे वापस डेटा नहीं भेज सकते, वही सेम डेटा नहीं भेज. That is what split horizon means.
Okay.
So that is why every time the switch is broadcasting it, it is not sending it back via the same interface, but it is sending to all other interfaces. This is called as the split horizon. So it's not a BGP specific thing. It's there everywhere.
ओके और एक क्वेश्चन था आप मतलब ये आपका इंटरव्यू सेशन देखा था मैंने अपने यूट्यूब पे डाला उसके ऊपर और थोड़ा नीचे. हाँ अभी यहाँ पे एक ही स्विच है. ओके लेट्स कंसीडर
There was a two. There was a I'll come to that question later.
No. My question is that if another switch is there, okay, and same scenario अगर होगा तो यहाँ पे कैसा हो रहा है? सेम एक ही स्विच होने की वजह से ब्रॉडकास्ट इज हैपनिंग ओनली ऑन द VLAN 10. लेट्स कंसीडर कि सेम टू सेम रेप्लिका होगा. ओके अनदर स्विच. तो ये जो थर्ड इंटरफेस है आपका वहां से ट्रैफिक जा रहा है. सो दूसरे स्विच पे जाने के बाद वहां पे भी 10 पे जाएगा या 20 पे भी जा सकता है? समझा ना आपको क्वेश्चन मेरा क्या मीन?
I got it.
हाँ.
I got it. Okay. Now. Okay. Anyone has any other question based on this topology? Anyone? No. Okay. Yeah, Mohit, you're saying something?
No questions.
No questions. All right. Now, let's, as Vivek was saying, let's make it as a two switch scenario. Okay. I have another switch. 1, 2, let me make this as 3, 4, 5, and 6. Now here I have 20. Here also I have 20, and this is 10. Okay, this is 10. So meaning that these two interfaces are part of VLAN number 20, This interface is part of VLAN number 10. Okay. Now, let's say PC number 1. Okay. PC number 1 sends a data. And again, let us imagine the two switches MAC address table is empty. Okay. So this is MAC port VLAN. Okay. PC number 1 sends a data. Okay. To the MAC address of 4444. Okay. Not 4444. Let me take that as 6666. 6666. Okay. So switch 1 receives the data. It makes an entry of 1111 received on interface number 1, part of VLAN number 10. Okay. Does it know about 6 in its MAC address table? No. So when it does not know about 6 in its MAC address table, it is supposed to broadcast it. And then it will check which are the other interfaces that are part of VLAN number 10. Now, it will forward it to PC number 3 because we have assumed that this is part of VLAN number 10. Now, if I want PC number 6 also to receive this data, one thing that I can do is I can configure 10 on each side of this switch. So what will happen? Now the switch will think I have whatever interfaces that I have that are part of VLAN number 10. I am supposed to forward it out of all those interfaces. So this is sent to switch number 2. Switch number 2 receives it. Switch number 2 sees it, right? And it also makes an entry, MAC address table, port, and VLAN, right? So here it makes an entry of 1111. It was received on interface number, let's say, let me 1, 2, this is 3, this is 4, this is 5, this is 6. This is 6 and this is 7. So it was received on interface number 4, and it is that interface number 4 is part of VLAN number 10, right? Then it will also check the destination MAC address, right? Is the destination MAC address known to it? No. So it will again broadcast it out of all the interfaces that are part of VLAN number 10. And here in this scenario, it is only one interface and it is received by 6. Okay. The respond back, the response from PC number 6 will also happen in the same scenario. But this time it will happen in a unicast fashion, because when PC number 6 is replying, the destination MAC is 1111 and the switches know about 1111 in their MAC address table. So instead of broadcasting, it is going to be unicast travel, right? So let me quickly go through that flow. So source MAC of 6666, right? So PC number 6 sends the data. Switch number 2 reads the data. It creates an entry for 6666 on interface number 7. Interface number 7 is part of VLAN number 10. It checks for the destination MAC address. Is the destination MAC address known? Yes. Via which interface? Interface number 4. And is that interface part of VLAN number 10? Yes. So it will forward it to switch number 1. Switch number 1 receives it. It sees the source MAC address as 6666. It makes an entry for it, and it was received on interface number 3, which is part of VLAN number 10. Then it checks for the destination MAC address. Is the destination MAC address present in its MAC address table? Yes. Is the interface part of the same VLAN? Yes, both are part of VLAN number 10, and hence it will forward. This is how the flow is going to happen. But in this scenario, what is happening is that if suppose PC number 2 wants to send a data to PC number 4 and 5, it will not be able to send. Correct? Because let's say PC number 2 sends a data 2222, right, to a destination MAC of 4444, right? This data is received. The switch makes an entry of 2222 and it was received on interface number 2, which is part of VLAN number 20. Then it checks for destination MAC 4444. It sees that 4444 is not there in its MAC address table. So it will look for all the other interfaces which are part of VLAN number 20. But in our topology, there is no other interface which is part of VLAN number 20, and hence here that data is going to fail, right? So in this scenario, again, what we can do is we can configure here as 20, these two interfaces as 20, and the flow is going to happen the same, right? But here the problem comes. Every time two different VLAN devices want to talk to each other, I will always have to change the VLAN numbers between the switches. And that is a very tedious task. So if I'm sending a data from PC number 1, which is connected to VLAN number 10, I will have to change this to VLAN number 10. If I am sending a data from PC number 4, which is part of VLAN number 20, then I will have to again go back and configure these two interfaces to VLAN number 20, which is a very tedious task for me. And hence, for this purpose, we came up with a solution. And that solution is trunk interfaces or trunk VLAN. There's no trunk VLAN, there is trunk interfaces. Okay, so what we do, we create these two interfaces as trunk interfaces. Trunk interface means that these two interfaces can carry not just one, but different VLAN traffic. Let's say it can carry VLAN number 1, it can carry 2, 3, it can carry 10, it can carry 20, anything. It can carry one VLAN data also, it can carry multiple VLAN data also. Now with this, what is going to happen? Let me redraw that diagram. Switch. PC number 2. I'm just drawing two. Oh yeah, let me draw 3 PCs. Okay. Now what I've done is I have created these two interfaces between the switch as trunk, wherein I can say that it can pass or it can accept data of both VLAN number 10 and VLAN number 20 on both the interfaces of the trunk. Now let's say what is going to happen. PC number 1 wants to send a data. Okay, let's say to PC number 6, which is part of VLAN number 10, right? So the source MAC is going to be 1111. Destination MAC is going to be 6666. Now let's see how the switch is going to work. MAC, port, and VLAN, right? So this data reaches switch number 1. Switch number 1 reads the source MAC address, makes an entry for it, interface number 1, part of VLAN number 10, right? Then it sees, it checks for MAC address of 6. It does not find it, and hence it is going to broadcast. But now when it is broadcasting, it will broadcast to PC number 3 because it is part of VLAN number 10, as well as it will broadcast it out of VLAN. Sorry, it will also broadcast it out of trunk port. But here, when it is sending it out of trunk port, it will also add a VLAN tag of 10. It will also add a VLAN tag of 10. Okay, and it will forward it to the switch number 2. When switch number 2 receives it, it will make that same entry. MAC address, port, VLAN, right? So it will make an entry of 1111. It was received on interface number 8, right? Now, because the data that is sent by switch with a VLAN tag of 10, the switch now knows that this data has come for VLAN number 10. Now, when it reads the destination MAC address and it does not see in its MAC address table, it will broadcast it. But because it read the VLAN tag in the incoming data, it will forward the data only to those interfaces which are part of VLAN number 10, and hence it will go to PC number 6. Okay. Any question in this flow? Any doubt, or do you want me to explain this flow once again?
My question is, why will it send to PC number 3?
Because PC number 3 is also part of VLAN number 10.
Okay.
But when it broadcasts, that time only it will send, right?
Yes, when it broadcasts, then only it will send. See here, 6 MAC address is not present in the MAC address table. So what is happening? This is an unknown unicast. Because it is an unknown unicast, it will treat it as a broadcast. So it will broadcast it only out of those interfaces which are part of VLAN number 10. So here, please understand, when VLANs are added, when VLANs are also into your equation of the whole topology, when the switch receives it, it will see, I am receiving a data on an interface which is part of VLAN number 10. That means my destination, or so not destination, my exit interface should also be a part of VLAN number 10 only. Or my destination MAC address should also belong to that same VLAN. So here, when the switch is broadcasting, it is broadcasting it out of only those interfaces which are part of VLAN number 10. And here interface number 3 or PC number 3 is part of VLAN number 10. And since this is a trunk port with VLAN number 10 added, it is forwarding it out of this trunk interface as well. Clear?
Yes.
Okay. Now the return traffic. PC number 6. When PC number 6 is replying, source MAC is 6666, destination MAC is 1111. Right. Now let's see what is going to happen. So PC number 6 replies, switch receives it, switch makes an entry 6666. It makes an entry for it, right? And it was received on interface number 456, interface number 6 on, right? 6 and 6 is a part of VLAN number 10, so it makes an entry for it. Then it checks for the destination MAC address. Does it know about the destination MAC address? Yes, that should be sent out of port number 8. And is port number 8 of the same VLAN? I received it on interface 6, which is part of VLAN number 10. And the exit interface, is it also part of VLAN number 10? Yes, it is also part of VLAN number 10. And hence, it will send it to the switch with a VLAN tag of 10. With a VLAN tag of 10. Switch number 1 receives it, right? When switch number 1 receives it, it will make an entry 6666, and it is received on interface number 7. And because it was received with a VLAN number of 10 tagging, it will add it. Then it will check, does it know about the destination MAC address? Yes, it is supposed to be sent out of port number 1. Port number 1 and port number 7 are part of the same VLAN. Yes, they are part of the same VLAN. And hence, the data is forwarded to PC number 1 directly. Okay, so please remember, whenever there is a trunk involved, okay, the switches will add the particular VLAN. Okay, so here in this case, what is happening? The receiving interface was part of VLAN number 10. And hence, when the switch is forwarding the data out of the trunk interface, it is adding the VLAN 10 to it. If the receiving interface, let's say PC number 2 is sending the data, and PC number 2 is connected to an interface which is part of VLAN number 20. So when the switch is forwarding this data out of this trunk interface, it will add the VLAN 20 to it. Now, why is this VLAN tagging necessary? Can someone explain me? Why is this VLAN tagging necessary? Guess, anyone?
You segregate the traffic.
Segregation has already been done using VLAN, right?
If trunk tagging is not there, means it will not other switch like second switch cannot identify it from which from which VLAN it is getting.
Correct. Right. So as I said, the trunk interface carries multiple VLANs, not just one VLAN. It carries multiple VLANs. It carries 1, 2, 3, 4, 5, 6. We can have VLANs from 1 to 4096. Right. It can carry these many VLANs. So when switch number 1 is sending a data to switch number 2, how will switch number 2 identify which VLAN does the traffic belong to? Right? Or if switch number 2 is sending the data to switch number 1, how will switch number 1 understand which VLAN does this traffic belong to?
Dangerous.
Right. Sorry. So until and unless there is a VLAN mentioned, right, the switch will not know. Because of the VLAN tagging only, the switch is able to identify the traffic, incoming traffic, and based on the incoming traffic's VLAN, it is able to make the forwarding decision. So switch number 1 over here received the traffic for VLAN number 10. And that is why it was able to make this comparison that the entry interface, right, and the exit interface, both are part of the same VLAN. Similarly, switch 2 was able to make that decision. The entry interface and the exit interface, both are part of the same VLAN. So that is why VLAN tagging is done when there is a trunk involved. Okay. Any question? Any question over here?
Untag means that access port wala traffic.
Can you repeat? Sorry.
So now you are saying if we configure trunk port, okay, or if any traffic is going to pass from the trunk port, that need to tag particular VLAN, right?
Correct.
VLAN information. So there are two ports, trunk port and access port, right?
Yes.
Access port is untagged, right? So if we configure both at access port on the say both switch end, so the traffic will pass without the tagging information, right? VLAN tag.
Correct.
Okay.
Correct. Correct. Okay. Any other question, Mohit? I saw you unmuted yourself.
It's clear now.
Now with this, let me ask you one question that I have been asked multiple times. Okay, and it's one of my favorite questions. Okay. So again, I think Vivek already knows it. Okay. So switch number 2. These both are access VLAN 10. Okay. And PC number 1, PC number 2. This is access VLAN 20. Okay. This is 10.0.0.1. This is 10.0.0.2. Okay. The question is, will these two PCs, will they be able to communicate to each other? Yeah, Mohit. We'll discuss this question tomorrow. Okay. However, this question is already there on my YouTube channel. I would ask you not to go to my YouTube channel and see the answer, but try to understand it yourself. Try to solve it yourself. Okay, and because we will be discussing this question tomorrow, right? So the question here is what the interviewer asks is they'll draw the diagram and they'll say there are two PCs connected to the two switches. Switch number 1 is part of VLAN number 10. Switch number 2 is part of VLAN number 20. Right? PC1 and PC2 are connected. Now, can PC1 ping PC number 2 or not? This is the question. Okay. So today's class, I'll stop it over here. Okay, we'll discuss this scenario tomorrow along with the lab.
Laksh, one more
Yeah.
question. One interviewer asked me.
Hmm.
So can you just draw it a single switch?
Yeah, sure.
A single switch, two PCs are connected. Okay.
Hmm.
Two PCs are connected. One is in VLAN 10, one is in VLAN 20.
Hmm.
They can communicate each other.
No. No, they cannot.
They can. If you connect two ports back to back and give one port VLAN 10 and one port VLAN 20, they can communicate.
On the same switch?
Yes.
I do not think so. I can also prove you with a Cisco packet tracer. It will not.
Back to back, I
how-
mean with the cable.
No, it
sir,
cannot. It cannot
when we are
connect.
saying back to back means on the same
What,
switch,
yeah,
right?
what do you mean? Yeah, exactly. What do you mean by back to back?
Mean cable to cable, like one port I will configure as VLAN 10 and other port I will configure as VLAN 20.
No, it cannot communicate.
No?
No, it will not. Okay, if you
How
want,
it
I
will
can show
forward,
you.
like,
I can show you right away on packet tracer. Because on the same switch, two different VLANs cannot talk. Okay, this will take time.
how it will
On the
forward
same-
when packet received from to the VLAN 10. Switch will broadcast to VLAN 10 only, right? It will not forward to the VLAN 20.
See, basically, this switch, it knows one of my interface is part of VLAN number 10. I will be receiving traffic on VLAN number 10. I will be sending traffic of VLAN number 10. This interface is part of VLAN number 20. I have to send VLAN number 20 traffic only or receive VLAN number 20 traffic only. So when PC number 1, let's say it says ping PC2, right? The packet comes here, right? It reads the MAC address. It knows that this interface is part of VLAN number 10. The destination MAC, however, is connected to an interface which is part of VLAN number 20. It will not forward. Both are two different VLANs. It will not forward. Even if you're saying if this is 0/1 is connected to VLAN number 10 and 0/2 is connected to VLAN number 20, even then it is not going to forward. It's not going to forward.
Okay, fine.
Okay, give me a couple of minutes. Let me log into the Cisco packet tracer and show you.
Yeah, I gave the same answer, but the guy was not,
Probably his question is wrong. It should be two. If it two switches, then there are possibilities. Okay, but with one single switch, no, not possible.
Have you asked him like why it will communicate to the interviewer?
yeah, I asked him like what you're trying to prove. It will create a loop otherwise. but he said like you can go and check it by yourself.
Okay.
Like that he just told me.
Okay.
I don't know. Yeah, Mohit. Yeah, you're saying you want to ask something?
Yeah, just wanted to inform you that the homework question which you gave me was asked in Juniper first round. It
Okay,
was
yeah.
asked
So
in
no
the
problem.
first round,
We'll
but
discuss
they
that
did
tomorrow.
not mention the VLAN tagging like you mentioned 10, 20 like that. They just asked me if we can ping PC1 to PC2, same IP address.
Same
Same,
IP address.
yeah.
Same IP? Are you sure it is IP?
No. I mean, the IP address which you have given to both the PCs were the same type of
Same
question.
subnet.
only.
Okay.
Same
Okay.
subnet.
Yeah. Yes.
लक्ष्य सर, मुझे जस्ट डाउट है अभी, जस्ट मतलब
Yes.
सीधी क्वेश्चन है कि I have VLAN 10 and VLAN 20. Okay. Can I configure same subnet on VLAN 10 and VLAN 20? Like 10.10.0.0/24 to VLAN 10 and 10.10.0.0/24 to VLAN 20. जैसा अभी
Same
इन्होंने
network.
क्वेश्चन पूछा ना, सेम नेटवर्क
Same.
बोला कि सेम नेटवर्क में पिंग कर सकते हैं क्या? आइडियली मींस एज पर, हाँ या सॉरी
Same. Okay. Same network में ठीक है. Like if the IP address is different, it's okay. 10.0.0. Like 10.1.1.0/24 has 256 set of IP addresses. Right, from 1 to 250. 1 to 254. You have different IP addresses, but they are different VLANs. You can have inter VLAN communication. You can do. It's okay. You that is possible. Okay, that is certainly possible. So let's say 10.1.1.1 is PC1, 10.1.1.2 is PC2. However, they two are different VLANs. This kind of setting is also possible. But again, because they are part of a different VLAN, they will not be able to communicate. Inter VLAN communication or router on a stick kind of scenario, that is possible. Let me stop the recording, guys.